All right, so this section is hypothesis testing for population standard deviation. So the good news is, unlike confidence intervals, hypothesis testing is all the same, right? It's just the same three-step process for the last two sections, right? You want to find your null alternative, you want to find your test stat, analyze it, and then find a conclusion. So it's pretty much the exact same process. So in other words, the only difference between the three sections, hopefully you guys noticed, is because, one is proportion, one is mean, and one's standard deviation. So for proportion, you're doing normal distributions, so z-scores. Mean, you're doing t-values because it's doing t. And now since we're doing standard deviation, it's going to be chi-squared, so the chi-square distribution. So literally the only thing that changes is step 2, right? Everything else is almost identically, based off that information. So when it comes to hypothesis for standard deviation, very little is different, like I said before. It follows the same exact process, except, we're doing chi-squared instead, right? And our parameter is going to be sigma, right? Because we're doing a population standard deviation, okay? So this actually is a little easier when it comes to finding the test stat. There's no square roots. In this case, we're just squaring a lot of stuff. So this is our test stat for our chi-square distribution when it comes to standard deviation. Okay. So this section is pretty short when it comes to it. Nothing too big a deal. Nice little breezy section when it comes to it. So we're just going to go straight into the questions itself, so you can see how that will break down. Okay. Right, so question 1 says, consider the claim that 10 supermodels have heights that have a much less variation than women's have in general. Use a 0.01 significance level to test the claim that supermodels have heights with a standard deviation that is less than 2.6 inches from women that have a sample standard deviation of 0.7997. Okay, and I cross it off because we're not gonna deal with it. And same thing over here. I have to say that. Just go ahead and cross out this this portion here. We're not even using p-values because of that. Okay. All right. So same exact thing as the last scenario, right? Step 1, we want to find our null and alternative hypothesis. So since it's standard deviation, we're using sigma instead, right? Instead of z's, p's, and mu's. So our portion is less than 2.6, so that's going to be equal to 2.6, and less than means strictly less than 2.6, right, our actual population. All right, so now we go to step 2. So for step 2, we actually need 3 numbers, n, s, and sigma. It's, one of the easiest ones because we only need 3 numbers. So n is always going to be the case of, the actual sample size, so that's 10 supermodels. S is given to us at the very end as 0.7997. And sigma, right, we wrote it down already, is 2.6. So to find our test stat, our chi-squared value, it's going to be 10 minus 1 times 0.7997 squared all over 2.6 squared. Okay, so if you do this in a calculator and slowly simplify, I believe you should get roughly a chi-square value of 0.851. Okay, and now we go on to the analysis. So since we're doing the chi-squared value, our graph is going to look like this, right? Okay, and remember, a chi-square value is the same thing as finding a t-value. You need an alpha and degrees of freedom. And since this test is a left tail test, which means we're going to be shading the left side, which means we're going to be finding the leftmost chi-square value. So go back to confidence intervals, and we'll talk about that right now. So first of all, let's write this down. Alpha is 0.01, and degrees of freedom in this case is 10 minus 1 is 9, right? So if you go to your tables, right, the problem is, remember, a chi-square value only gives you the area to the right of it, but we want area to the left. So we have to tweak that when it comes to it. So instead of actually using the alpha 0.01, we're going to use the alpha of 1 minus 0.01 because we want everything on the left-hand side. So the new alpha, I'll call it alpha nu, is 0.99 instead because we want the leftmost value over here. So if you guys look at your format sheet, let me pop that up so you guys can see it. We're going to go to your chi-squared values, which is your 3rd page, I believe, web page. Okay, so we're going to use 0.99 instead because that's the left one. go down to 9 degrees of freedom, and that is 2.088. So our critical value is 2.088, and it's going to look like this. Okay, and now we do the same exact concept. So remember, chi-squared goes from 0 to infinity. So is our chi-squared value within 0 to 2.0? Definitely yes, right? So that means we will reject our null hypothesis. Okay? And we do the same exact conclusion, right? Go back to your portion. So I'll quickly show you guys. Just like over here, go all the way down. Right, in the same exact process. So we would say no doesn't have equality, says less than, and yes, we reject, so we should be in box 3. The sample data supports the claim that, we go over here, supports the claim that the heights of, or is it, that superbowl heights have heights with a standard deviation that is less than 2.6 inches for women that have a sample standard deviation. Okay, so roughly the same tempo, which is nice. And again, the only thing that changes from section to section is exactly just this part right here. Okay. So let's try the next question down here, question 2. So question 2 says 25 cigarettes were obtained and measured for a tar contents. The sample had an S equaling 3.7 mg, so milligrams. Use a 0.05 significance level to test the claim that the tar content has a standard deviation different. This is interesting, right? Different from 3.2 milligrams. Okay, so we'll just go do the same process. So this is going to be equal to 3.2. And different means not equal to. Okay. So now we go on to step 2. N is how many cigarettes? So we did a total 25. S is 3.7. And sigma is 3.2. So our chi-squared value is going to be 25 minus 1. 3.7 squared all over 3.2 squared. And if you do this, I believe you should get a chi-squared value of 32.086. That's what I got. Okay. And now we do the same thing, right? Go back over here. Okay. Now, because now this is a two-tailed test, right? Not equal to, so two-tailed. That means just like everything else, we're shading both sides. And guess what? Just like we did for the t-values when it comes to two-tailed test, we have to cut alpha in half. So since alpha is 0.05 in this case, we cut it in half. Therefore, it's going to be 0.025 and degrees of freedom of 24 in this case, right? So remember, now we're going to have two chi-squared values. Well, guess what? We already did this before when it came to confidence intervals, right? Finding the left and also the right one. So it's the exact same process. So let's just do the easy one, the right one. So we're going to go with alpha 0.05 and degrees of freedom of 24. So using our formula sheet. So 0.025 degrees of freedom of 24 down here. So our first one is 39.364. We see that? That's the first one here. Now to get this one, here, we do the exact same we did on top, right? We do 1 minus it. So 1 minus 0.025 should give you 0.975. So we're going to use that alpha and the same degrees of freedom. So notice it's pretty much swapping right now there. Notice the same thing. So go 0.975 down to 24 degrees of freedom, and this is now 12.410. Remember, since it's a two-tailed test, we have two different chi-squared values, right? Because it's the left and the right one. So now we do the exact same thing. So 32 is roughly over here, right? So since it's not within our ranges, right? It's not in the shaded region. So this means we do not reject H naught. Right? Don't reject it because it's not within our critical regions we're looking for. So therefore, if we go to our conclusion, so first, does it have equality? Well, it says difference, so no equality, right? Difference not equal to. Do we reject? Nope. So there is not sufficient sample evidence to support the claim that the tar content has a standard deviation different from 3.2. Okay, and that's it. So, it's a pretty quick section when it comes to it. As long as you're able to get the boundaries, you'll be A-okay when it comes to this. Okay, and that's it.